Welcome everybody to another session, to another webinar. First of all, if you do have any issues about video or audio, please use the chat function, and also for your questions, please write them in the chat and I will answer them after the webinar. So today we will talk a little bit about the TDR sensors, about the TDR technology, and in this case we will have a look at some difficult process conditions that can be solved with TDR sensors. So this is what we will talk about today. So we will start with why we call it a universal technology, this TDR, and I will give you a short portfolio overview. I will talk a little bit about the technology, a little bit deeper into detail, and then we will move on to the challenges, on the one hand in solid applications and on the other hand in liquid applications, and interface measurement, and we will talk about the advantages of a special type of probe, the coaxial probe, and then we will have a look at some extreme conditions and what TDR sensors are made for those extreme conditions. So TDR sensors, this is you can use them very versatile in many types of applications. So it's a universal technology. So the uni stands for uncomplicated, normal, intensive. So we can use it in for the uncomplicated applications. So these are simple storage applications which require a reliable and durable solution. And what is important, it should be easy to install and easy to use. So TDR sensors do have a quick setup, so very simple to install, and also the adjustment is not material dependent, so you can adjust it whether there is material inside the tank or not. So very easy to use, and it does not matter what type of vessel they are installed in. They can be installed in metallic vessels, in concrete vessels, in plastic vessels. The size of the vessel does not really influence the measurement. So it's very easy to use and easy to install. Then we have, on the other hand, some normal applications. So these can be storage or process applications. And here we need a solution that can cope with the common challenges. So like temperature, pressure changes, dust, steam, condensation, humidity, and these are some typical common challenges you are confronted in solid or liquid applications. And third type are the very intensive applications. So where we do it have maybe an interface measurement, high temperatures, high pressures, and when we need a quick reaction time, maybe you have installations inside the tank like mixers or something else, you can also use the TDR technology in those type of applications. And what we have TDR sensors, especially made for solid applications. What we offer is the NivoGuide 3100 with rod rope or PA coated rope, but we will come to this later on a little bit more into detail. What portfolio we offer, but basically one for solid and one for liquid applications. So NivoGuide 8100 and 8200 with 3 different type of probes, rod rope or coaxial. So when we're now having a closer look at the technology, so first of all, the sensor, what is basically are the components is the housing, the coupling, and as I already mentioned, the probe. And we do have sensors for solids, for liquids, for higher demands, and then for the high pressure, high temperature applications. They differentiate in some features, what I here noted in green. So for solid applications, we have a coated robe, and they are built more robust, that they can withstand all the forces which are working on the probe. For liquid applications, we have a special type of probe, so the Coaxial Probe, and this offers a greater stability and also a better signal strength, so we can measure materials with a very low decay value. And we have many more advantages of this Coaxial Probe, but also this will be explained later on in the webinar. And then we have two types of sensors. They are for the higher demand, so one middle class, I would say, so up to 100 bar and 250 degrees. And on the right hand side, we do have then the very high class sensors made for high pressures, so up to 400 bar, and very high and also very low temperatures. So you can see this big range, so from minus 196 to 450 degrees Celsius. So very robust sensors. All come with ATEX approvals and also with seal. And the high pressure versions are also certified for use in steam boilers. As I said, we have different types of probes. So we have the rope probe, sensors with rope probe. They can be made very long. We have an option as a coating, so they are easy to ship and easy to mount. Also, when it comes to longer or higher silos, they can be fixed on the with the tensor wide, and they can also be shortened and cut to the length which the application needs. In the middle, we have the rod probe, so they can be made for lengths up to 6 meters. So the minimum length is 300 millimeters, so a wide range. So for very small, but also bigger vessels, you can order the rope in segments, so it's easier to ship and also to install. And as we already had it for the rod version, the rod can also be shortened on side, so that you are very flexible with whatever height you need or whatever length you need. You can cut them on side. And on the right hand side, the third option, so we have this coaxial probe, can be also configured up to 6 meters. It's used for special applications. And the big advantage is that the pulse is really focused inside this tube. So the signal strength increases and it's more sensitive for medium with lower decay values. So what happens when we're measuring a level with TDR sensors? So we have a microwave pulse that is generated by the electronic and is coupled onto the probe. So as we had it in the slide before, the probe can be either a rod, a rope, or this coaxial version. And due to this skin effect, the pulse travels with the speed of light along the probe. And the effective radius of the energy this pulse are 500 millimeters. So the energy spreads in a radius of 500 millimeters around the probe. And as soon as this pulse then reaches the material, some parts of the energy of this microwave pulse get reflected and move back to the sensor. And this reflected pulse is then recognized by the electronic and processed into a level measurement. So here we can see how it basically looks. So when the level reaches, the pulse gets reflected and reaches again the sensor. So the pulse to pulse time is always the same, but when the level is higher, the time difference between sended and reflected pulse is shorter. And here we have some basic information about the microwave. So it's electromagnetic. It travels under normal conditions. So when we have air, it travels with the speed of light. This is an important property of this microwave pulse for the level determination. And what also is important to know that 80% of the energy we are sending out is really focused near the probe, so in around 200 millimeters radius. Although some parts of the energy do spread, so that we have this effective radius of 500 millimeters. Two important factors are influencing the accuracy of this measurement with TDR technology. So on the one hand, we have the running time, also known as the time of flight. So this is the time a microwave pulse needs to travel up and down the probe. And what influences this time is the speed of propagation, and this is normally in air, it's the speed of light. And with those two parameters, we can then determine the distance from the top of the vessel to the surface of the medium. So what is measured? Measured is the running time, so how long it takes up and downwards. What we know is the speed, so we have the speed of light, and with these two parameters we can then determine the distance, and with the known tank height we can then calculate the level of the medium. Speed of propagation, important factor, normally speed of light, and these are also the calibration conditions. So we calibrate those sensors in air, the ambition medium of air, and this is the default value for the speed of propagation is the speed of light. And this speed of propagation is influenced by the medium and its decay value, or where the microwave travels through. This is then important for interface measurements because there the speed of propagation decreases, but we'll come later on to this topic. So this is how it looks like, and here you can also see that as soon as the microwave reaches the medium, it travels a little bit inside the medium, but the speed of propagation decreases. Well, we're now comparing two echo signals. One important factor is the decay value of the medium, because this influences a lot how the echo signal looks like, and also the reliability of the measurements. So when we have medium with high decay values of greater than 10, examples are water-based liquids, related acids, or lye. So the amplitude is of the signal reflections really big, because we get a lot of energy reflected from materials with high decay values. And also when a microwave propagates through the medium, because some parts are reflected of the energy, some other parts penetrate the medium, the damping is very strong of medium with high decay values, and the penetration is weak because of the strong dampening. So we do not see the end of the probe, so the microwave does not reach the end of the probe in a medium with high decay value. On the other hand, when we have a low decay value, medium with a low decay value, like most of the bulk solids or plastics, and oil-based liquids. The amplitude is small of the signal reflection because less energy is reflected. And the medium penetration is strong because the microwave can penetrate materials with low decay value very, very easily. And it also reaches the end of the probe. So at the end of the probe, we do also get a negative downturn. This is what we can see here, this negative downturn. Here we can see the end of the probe. And this is also recognized by the sensor. So this is basically also an important feature. So we now talk about the challenges in solid applications. We now know how measurement, how this technology works. And now what are the typical challenges in solid applications? So here are 4 points. So most of the applications can be very dusty, a very, very dusty environment. Then we can have some materials that are quite sticky because of environmental changes, and the material might build up around the probe. Narrow or high silos, and also in solid applications, with heavy materials, we get a high force, a high tensile force onto the probe and then also onto the coupling. So what are the TDR specials? One special is the low frequency of the microwave. So because dust also dampens the signal a little bit, and this dampening is depending on the outstanding frequency. And TDR sensors are basically also radar sensors, but with a lower frequency than all the non-contact radar sensors operate. And so this is an important point, the low frequency, because we do not have a strong dampening due to dust, and also the speed of propagation is not influenced. So with TDR sensors in dusty environments, we get a reliable and also very, very accurate measurement. Build-up. What is the effect of build-up? So build-up reduces the signal strength because it dampens the energy, and it also decreases the speed of propagation. So build-up should be avoided around the probe, and what we do, we have a special probe design, so it's really, really clean and smooth to not get any build-up around the probe, or to make it more difficult that build-up can form around the probe. The effects are less build-up, and also TDR sensors can deal with a small layer around the probe, and this small build-up does not really influence the measurement. So again, we have accurate measurement results when we avoid build-up around the probe. High and narrow silos. So what is here the advantage of TDR sensors? The advantage is that we always know the effective radius or where the energy spreads. This is always in around this area of the effective radius, always around 500 millimeters around the probe. And this pulse does not enlarge. When we think of non-contact radar sensors, they send out the energy with a certain beam angle, and this beam angle increases and the higher the silo is. So in lower areas, when we have installations here, we do not have any risks of fault echoes due to these installations, and we do never hit the side wall of the silo because we are always having this 500 millimeter effective radius. So the signal is always good and not influenced by any false signals due to installations. And this makes also finding the right spot for the sensor mounting easier, because we always know where the energy really is and how big the effective radius is. So we have less downtime due to false echo signals and also a reliable measurement. Third point is this really robust design of the TDR sensors made for solid applications, because when we're having heavy materials, heavy bulk solids, we get a little bit of force onto this probe that works on this probe here and also on this coupling. And with this robust design, we can withstand tensile loads up to 30 kilonewtons. So pretty much, and you do not need to concern about any probe damages or any breaks of the rope because of this robust design. Three other challenges in solid applications. You can find always this bulk cone. So we have not a flat surface, and also the bulk solids do have a low decay value. And those two elements, so this bulk cone and the low decay value, influence the reflection of the transmitted electromagnetic pulse. So bulk cone, bad signal surface, and low decay value, a weak signal reflection. What's the advantage of TDR? TDR sensors to guide the signal along the probe. We do not lose any energy reflections due to this bulk cone, and also for the lower decay values, this is important because you need as much as the energy gets back. So the more energy gets back to the sensor, gets really back to the sensor, is not lost due to this bulk cone reflection, reflected away and does not reach the sensor electronics, the better it is. So with this guiding, we do get better, stronger signals, stronger reflection signals, and this also then again causes more accurate and also reliable measurement results, even in materials, even in bulk solid applications, where it's hard to get a good signal. But with this guiding, the signal strength is improved. And one last feature, in some applications, the decay value of the material can change. So due to humidity or moisture or temperature changes, this may lead to a change in the decay value of the material. So the more dry it is, the lower the decay value. And this is also recognized by the sensor. And then this is called the probe end projection. With this feature, the level is then determined indirectly. So you get always a signal, even if the decay value changes. And so you have a reliable measurement and do not have to care about any decay value changes due to humidity or some other environmental conditions. So these were the solid challenges. When we're having a closer look to liquid applications, what are here the challenges? So steam, condensation, and foam, typical challenges. So here again, steam can be compared with dust in solid applications. Steam may dampen the signal, but due to this low frequency, we have a low dampening, and we always get a good signal back from the medium. And the dampening is quite weak, and we do not have any impact of the speed of propagation. So the measurement will stay accurate even when it comes to steamy application. Condensation may also be an issue, so condensation can form at the process connection, and here a condensate cone is implemented to avoid any short circuits between the process connection and the probe, because if we have condensation here, the spread of the energy is influenced, so we do not get the signal sent out. And with this condensate cone, this problem is avoided, and we do not get any incorrect level jumps to 100%. So a good feature, to make the TDR technology also work with condensation. Foamy applications are, a little bit more challenging, because we do not have the foam does not really exist. It is there are different types of foam, and we can never say, okay, if we have foam, it will work. But what's the advantage of TDR sensors here again is the low frequency. This is what you can see in this diagram here, the frequency, and on this axis we have the signal damping. So the lower the frequency, the less the signal is damped. So for application where the foam should be ignored, TDR sensors are the perfect solution. So if you want to ignore the foam and only have the real surface of the medium, the TDR sensors are the best solution for those types of applications. We'll now move on to liquid applications, which we can solve with the special type of probe, so with this coax probe, and also talk a little bit about the coax effect. So what's the basic advantage of this coaxial probe is, you can see it here on the right side, that the energy is really focused inside this coax tube. So it does not spread in around 500 millimeters, but focused inside this tube. So this is big advantage when we're having like narrow vessels or installations inside the vessel. So this is what you can see here, because when the microwave pulse reaches such an installation, then we get a reflection from this installation, and this can be avoided by using the coaxial probe. So here all the energy is focused inside this tube, so we can ignore any installations and get the best result, the best measurement results with this coaxial tube. So you do not have to matter about any installations inside the tank. Also here, when we have like mixers inside the tank, the blades may also cause false echoes or echo reflections. And another effect is that we have strong turbulences when it comes to the mixing process. And what makes the coax also is very stable. So you do not have, there's no need to concern about any damages, because this coax tube is very robust and protects the probe from getting damaged, and you can ignore the blades. So no need to concern about any false echoes, and no need to concern about any probe damages. Third point, small vessels. So as you can see here, this vessel is very small, so it's half a meter. And TDR sensors normally do have like a dead band in the upper area where no measurement is possible. This is reduced by using a coax probe to a minimum of 30 millimeters. What you can see here, and with this 30 millimeters, it's possible to really measure up to nearly the top of the vessel or the top to the process connection. And it can be also installed in this little tube, so in these bypass elements. This has the same effect like the coax tube, just focuses the microwave, it increases the signal strength. So with this type of installation, you're again always on the safety side. So this will give you a really, really reliable measurement. Another effect is that due to this focused signal, we get a improved signal strength. So the signal is better than when it's spread only around the probe. But when we focus this signal inside this tube, we can also measure liquids with a very, very low decay value. So like solvents or liquefied gases, they normally do have a very low decay value, and by using the coax tube, you will have reliable and accurate measurement results, even with this hard to measure liquids or materials. So we can also measure medium with lower decay values than 1.5 by using this coaxial probe. So many, many advantages when we use this coax probe, and with this type of probe you will get the most accurate results and the most reliable results that you can have with TDR sensors or with radar sensors. Another special of TDR sensors is the property that they can be used in interface measurements. Why can they be used, or what is the which conditions have to be met? So there are 4 requirements to use TDR sensors for interface applications. So we need a certain thickness of the upper layer. So in this case, oil should be minimum 50 millimeters. The decay value needs to be known. The decay value of the upper layer shall be smaller than the one of the lower layer, and the difference of those decay values should be greater than 10. So here oil normally has a decay value of 2, water is 80. So a typical interface application where TDR sensors can be installed perfectly. What happens? So we generate 2 echo signals, so one small from the oil surface and one greater from the water surface, and the speed of propagation reduces inside the oil layer, and when it reaches the air it decreases again. So that's why we need to enter the decay value of the upper layer to recalibrate the right speed of propagation, and with entering the decay value of the oil surface we get a reliable measurement result. So two measurements, one total level and the other from the interface, and both are quite accurate. Another important factor is the bandwidth. So the bandwidth is important to separate 2 echo signals from each other. As I said, we get 2 echo signals, one from the oil and one other from the water surface, and the greater the bandwidth, the better those 2 those 2 echo signals can be separated, and the more reliable the measurement will be, and the thinner this upper layer can be. So this is basically the reason why the Nivo guides can measure such thin oil layers lying on top of the water surface. This is because of the high bandwidth of the sensors. Last point, high temperature, high pressure challenges. So here also TDR sensors are made for. These are these very robust sensors. So the sensor design is really robust, and also when you like lifting such a sensor, it's very heavy because this design. So with touch sensors, you can measure in the most extreme applications, so with the temperature range and also with this high pressure up to 400 bar. And although we have this long coupling, and the microwave has to travel a long distance through this coupling until it reaches the probe and then gets spread out, we have a good signal, or the very reliable signal that can be sent out because of this optimized coupling construction, and long lifetime and reliable measurements result are guaranteed by using this type of sensors. And where they are basically installed are steam boilers. In steam boilers, we have another challenge is the steam. So steam in combination with high temperature and also high pressure has in a certain area a big influence on the speed of propagation. So what we do here, we have a special feature that's called the steam compensation. So with this feature, we can eliminate this reduced speed of propagation, because we're getting a smaller tube around the probe. This is what's installed here. We get a reference signal, and with this reference signal, this reduced speed of propagation can be eliminated, and the right speed of propagation is determined with the use of this reference signal. So this is basically what happens in the steam compensation. An additional small tube is installed, get reference signal, and with this element, then we can have, or we get reliable, very accurate measurement results, even in such challenging and extreme applications with these extreme conditions and with steam superimposed over this liquid surface. So this was basically the overview of the TDR sensors we are offering, so for solid, for liquids, and also for high temperature, high pressure applications. The different challenges, what happens, and why TDR sensors can be used for those challenges. I hope it could make it a little bit clear. What I have in the end are two success stories, what we already installed. So we had one TDR sensor in the wood industry. So this was installed in this little bypass tube. So a very small vessel with 600 millimeters. And it was this high viscous product. So it was resin water. This came from the heating of the lugs in the dryer system. And we get this resin water. And we installed the Needle Guide 8100 here, not with coaxial probe, but it has the effect of this coaxial probe in such a bypass, and it worked perfectly. The customer was very satisfied. And another one, a really extreme application was, what you can see here. So in fish remains, so we had to control the material flow in such a small vessel here. And this is how it basically looked inside. So we had installations inside the tank on the left and on the right side. So what we did, we used the coaxial probe. And what we also had, like this sticky material, the fish remains. And the customer also installed a tube around the coax probe, and this does not have any influence on the measurement, but protects bigger fish remains to stuck inside this coax probe, and this worked perfectly. Also, you can see here there was also very much foam that formed, but the NeoGuide worked perfectly, and the customer was very satisfied with the solution here. So with these two success stories, I come to the end. So this was the session for today for TDR sensors. If you do have any questions now, or maybe when they come up later on, just contact us, contact me, and then we will find always the right solution for the applications, always the right TDR sensor for the challenges you have. And I hope that I could give you some helpful information about the technology. And I see that we do not have any questions. So thank you for your time. And I hope you will join the upcoming webinars. We are planning to do some more this year. So I hope to see you there. Have a good time until then. And thank you for your time. Bye-bye.